All right, you're all welcome to Qiskit Forfeits Ghana version day 3. We are excited to have you join us from all over the globe. The theme for Qiskit Forfeits Ghana is quantum computing for social good. How do we apply quantum computing in our society? That is our theme. So we are looking forward that after this workshop, discussion on applications will be made in Ghana, Africa, and the world at large. We would like to welcome all of you once again. Thank you so much for being with us from day 1, and today is day 3. I am so excited. I guess I have moved from ground energy level to the excited state. And I'm sure most of you may be quantized by now. So let's get entangled together in our breakout room. Let's get to know each other. Let's get to share wonderful ideas. Thank you as we move to our breakout rooms. I guess we are all back from our breakout rooms. Anyone wants to share anything with us? If you'd like to share something with us, I mean, you can unmute yourself and go ahead and share.
Hi.
Hi, Ahmad.
I want to ask one thing. Am I audible clearly?
Yes,
you can. Yes, you can go ahead.
Yep.
Yeah. So I want to ask, like, we have so many software development kits, like Qiskit, Pennyline, or let's say we have D-Wave quantum computer. So for all of them, which one is better, or in which one could be more universal? Would it be a D-Wave quantum computer or a gate-based quantum computer?
All right, Dr. Nimbe, please, would you like to take that?
I'm not sure I heard what he said. Did you hear?
Can I get a question again? I didn't hear what he said.
Obviously, if you did, can you help us?
Ahmad, can you repeat? Because I got it, but for the sake of the other people.
Yeah, so let me rephrase it. Like we have so many kind of quantum computers like gate-based and D-Wave quantum computer. Also, we have, for example, superconducting quantum computer. Or so, which one is best in this era, or which one would be the universal, like gate-based or D-Wave for and for purpose of use?
Okay, so if I get you right, are you asking which will be best, whether Qiskit, D-Wave, or?
Yeah, so yeah, that was kind of like which one be the more universal in the
Maybe
case of
Dr. Nimbe, you
use?
can help us.
Okay, can you hear me?
Yes.
Yeah, so as it stands now, there are a lot of platforms, a lot of technology in place, superconducting qubits, ion trap, and so on and so forth. But all of these are still in the developmental stages. We still have a very long way to go. But as it stands now, superconducting qubits, per my research, has actually made a long way in progress when it comes to the quantum computing field. And I'm sure IBM also employs that particular technology. So you realize that even the most popular framework is Qiskit. If you compare Qiskit to SEC and Microsoft Q# and all of that, you realize that Qiskit has made a long advancement when it comes to quantum computing frameworks. So the superconducting qubits, to my perspective and per my research, seems to have made advanced progress. Yeah, so the gate-based approach to is also what is widely used worldwide. So that is my answer for you. I don't know if you are okay.
Yeah, I got. Thank you. I'll also do some kind of research.
Great. Any other comments before we kickstart? Okay, so it seems like no more comments, no interference, and I mean superposition is in place in this virtual meeting. I guess you're ready to get entangled and get to teleport some knowledge here and there. And today we are so fortunate to have Dr. Peter Nimbe to take us through our lecture for day 3. So Dr. Peter Nimbe, we are ready for you.
Okay. Thank you very much. So before I begin anything today, I want to do a recap of what transpired yesterday. So yesterday we spoke exhaustively on what Qiskit is all about. We talked about various frameworks that are in place in different locations and areas, but we stated that Qiskit is the most widely used framework. And then even though we have other frameworks like SEC and all. So if you want to move into quantum computing, you want to program circuits, algorithms, you want to do even machine learning, quantum machine learning and everything, Qiskit is the way to go. I've explored it and I know that there are a lot of things in there, a lot of libraries in there that you can use to make your work very, very simple. So kudos to IBM for the Qiskit platform. It's a wonderful platform that everyone should actually explore and make use of. Now we move from there. We talked about classical gates, and in classical gates we looked at the basic logic gates like the NOT gate, the AND gate, the OR gate, and then the XOR gate. So we also spoke extensively on what these gates is all about. I'm hearing some sound at the background. Can we all mute? Okay. I hope I'm so audible. So we spoke extensively on classical gates and what classical gates is all about. We talked about the AND gate, the OR gate, the NOT gate, the XOR gate. And we said concerning the fact that there are times you can actually combine multiple gates together to produce a particular output. So you can combine a NOT gate with an OR gate and you get a NOR gate. You can combine a NOT gate to an AND gate, you get a NAND gate. You can combine a NOT gate to an XOR gate and you get an XNOR gate. So it is possible to combine gates together to get desired outputs and outcomes. So from there, we took a look at quantum gates. And quantum gates, we explored various gates like the poly X gate. And we said that the poly X gate is just an equivalent of the NOT gate that is used in the classical computers. So if I want to change a 0 qubit to a 1 qubit or a 1 qubit to a 0 qubit, all I need to use is the poly S gate. We spoke about the poly Y gate, the poly Z gate. We said the poly Y gate is basically operates like the poly S gate, only that this time around we are moving through an imaginary axis, and that is what differentiates the poly S gate from the poly Y gate. We took a look at the poly Z gate. We looked at the Hadamard gate, which is used for superposition. That is placing objects in multiple states. We looked at the C0 gate, which is used for entanglement. And I spoke exhaustively on all of these. So it's just a recap. I'll share my presentation on whatever I'll be doing today. So I'm just trying to recap what I did yesterday. So we also looked at how we can look at some transformations when it comes to the various gates. You say the various gates actually have some mathematical matrix that you can actually make use of. So every gate actually is a matrix. So you can use the matrix against a particular qubit or use it against some vector to get a particular output. So I'm going to be sharing my screen shortly, and then we explore some of the things that we did yesterday. We continue and explore one or two gates today before we take a look at the Quantum Enigma. So let me share my screen now. Okay. So I talked about let me choose a brush. Okay. So I talked about the poly-S gate, which you said is represented by this matrix. I also spoke about the poly Y gate, which I said is represented by this matrix. Then I spoke about the Z gate, the poly Z gate, which is represented by this matrix. So you can apply these matrices with qubits, which also can be represented as vectors, and then you get some desired output. So for example, let's take a look at some of the qubits and the transformations that we looked at yesterday. So we said that if I have a 0 qubit and I have a 1 qubit, the vector, this can be represented as 1, 0 vector, that's a 0 qubit, and the 1 qubit can be represented as a 0, 1 vector, right? So we spoke about how to utilize these vectors together with matrices in order to get some desired output. So I could want to transform 0 to 1 qubit. All I need to apply is the poly S gate because it's the equivalent of the NOT gate in classical computers. So poly S gate is used to transform 0 to 1 when it comes to quantum computers. So all I need to do is just combine this vector with a matrix, and then I'm good to go. So I could have a matrix 0, 1, 1, 0 combined with the 1, 0, and then I do my computations and realize that it results in one vector, one qubit. So that is how you can actually do those transformations. So you can do them mathematically, you can also do them program-wise. So we looked at how we can do all of this mathematically. We also looked at how we can do them by means of writing programs using the IBM Quantum Experience or the Qiskit platform. So that is it. Now let's take a look at the Hadamard gate. We also spoke concerning the Hadamard gate, where we said that if I have something like this, I can have something like this. This is usually the plus state, and this is usually the minus state, right? So this is just a block sphere that I'm trying to draw. It's not looking like a block sphere, but I'm sure you can take it like that. So when you have something like that, it's a plus state. If you have something like this, it is a minus state. And the Hadamard gate is used for superposition. So anytime you want to place objects in a superpositional state, you need to use the Hadamard. That is what you normally use. So it's used for representing objects in a superpositional state. We also took a look at the CNOT gate, and we said the CNOT gate is used for entanglement. So you can have the CNOT gate, also known as the controlled NOT gate. So we use the CNOT gate for entanglement. So if I want to entangle two qubits, maybe 0 and 1, then you use the CNOT gate. So that is what is used for entanglement. And we've realized that entanglement is one of the basic properties when it comes to quantum mechanics. We spoke about it yesterday, and Lauren made mention of it. We have superposition, we have interference, and we have entanglement. So if you want to depict entanglement, we always use the CNOT gate to do that. So you realize that it always requires two parameters. One of the parameters is a control qubit, and the other one is a target qubit. So that is what we spoke at length yesterday. For today, let's take a look at the swap gate. I'm sure many of you have heard of the swap gate. And the swap gate is normally used for exchanging, as in swapping two or more things. In classical computing, we talked about the fact that you can exchange the contents of two variables. Or let's say I have a cup. This cup is X. I have another cup. This cup is Y. If I place tea in here and I place coffee in here, I want to interchange these two cups. Then I need a third cup called Z, so that I can pour the contents of one of these cups in there, and then I can pour this in there. So to do this particular exchange or interchanging, you need a third variable, a third cup in this situation. So we are doing what is known as swapping. We are performing some form of a swap. So if you want to perform a swap between these two cups, then in quantum computing, we said we are going to use the swap gate to do that. If you want to swap things in quantum computing, you have to employ what is known as the swap gate. So the swap gate have a structure like this. We have something, yeah. So let's see how we can utilize the swap gate our advantage. So let me go to the IBM platform, and then let's see how we can utilize the swap gate. So as usual, we are supposed to import our libraries. So from Qiskit, import quantum circuit because we are dealing with a circuit. So we are going to create a quantum circuit object called QC. Now this object is accepting 2 qubits and 2 classical bits. So I stated yesterday that a quantum circuit can have just one parameter or can have 2 parameters. If you have one parameter, then we are dealing with the qubits. I have 2 parameters. We are looking at qubits and classical bits. So I want to actually show what the quantum circuit is all about. So QC equals quantum circuit. That's a quantum circuit object. As soon as I get a QC, I can actually, so what I'm trying to do is for the first qubit here, I'm trying to initialize or set this qubit to a 1 vector, and I'm trying to set this Q1 to a 0 vector. So in order to do that, we have to initialize, we need to have a variable called initial state where we pass it a list. That list contains a 0 and a 1. So we said qc.initialize, then this initialize function, we're going to pass the initial state 0, 1 to it, and then we say comma 0. So meaning on qubit 0, we want to initialize it to a particular state or value, and that is the 1 qubit that we see here. So we also want to initialize the second qubit. So we just have to repeat the same thing, but this time around, instead of passing 0, 1 to the initial state variable, we pass 1, 0 to it. So you realize that 0, 1 is actually a 1 vector, and 1, 0 is a 0 vector. If you still remember, right? If this 0, 1 is actually a 1 qubit and 1, 0 is a 0 qubit. We've explained this several times. So this 1 qubit, I'm trying to set 1 qubit on the qubit 0. That is known as Q0. And I'm trying to set the 0 qubit on the qubit 1. And that is what we are seeing here. So you realize that I set this state to 1 and I set this state to 0. So let's perform a swap. If we perform a swap between Q0 and Q1, then Q1 should now be a 1, and Q0 should now be a 0. So you realize that after the swap gate was actually applied, we now have Q0 to be a 0 and Q1 to be a 1. Obviously, if you measure anything in quantum computing, the state collapses to a classical nature. So I explained this yesterday concerning the collapse whenever you perform some measurement in quantum computing. So that must be understood in that perspective. So let's go back to our code. So that is how to actually set the initial state of a particular qubit. If you want to set initial state or some initial value, you always do something like this. So all this code is saying is that set my qubit 0 to the 1 qubit and set my second qubit to a value of 0. So once the settings has been done, you can now perform your measurements using qc.measure. So we are actually measuring the qubits, but in measuring them, we need to measure it onto the classical bits. So that is how come we have 2 lists in between the measure function. So this list is actually the quantum, and this is a classical component. Yeah. So after measuring, we can actually perform a swap gate and all of that, and even draw. So you can decide to even perform the swap and also run this, and let's see. Yeah. So you bring it before measuring, it doesn't really change anything. So that is how the swap gate is actually used. It's used for swapping things. So if you want to swap anything in quantum computing, just use the swap gate and you are good to go. Yeah. Then we also have what is known as the identity gate. Actually, the identity gate does nothing in quantum computing. All right. The identity gate does nothing. Identity gate represented by I. So we can have the matrix representation to be a 1001. The identity gate. Identity gate usually does nothing. But then somebody will ask, so then what is the use for identity gate? So identity gate is normally used in calculations, right? It's normally used in calculation. For example, if I want to prove that the S gate is its own inverse, the poly S gate is its own inverse, I can use the identity gate to do that. And also, if I want to make, I want to specify a null or none operation in a particular hardware, then I can also use the identity gate. So yes, even though it doesn't perform anything, but it's very, very useful when it comes to computations in order to prove that something is its own inverse. And also, if you want to specify a non-operation in a computer hardware or something, you can also use the identity gate to do that. But it's very, very important we take note of the identity gate. So for the poly S gate, if I just apply two of the poly S gates, I can actually get what is known as the identity gate. So it's just to say that the poly S gate is actually can be its own inverse if you want it to be so. So that is what the identity gate is all about. So I've spoken about the swap gate and I've spoken about identity gate. I don't know if there are any questions before I proceed. Okay, any questions? If we are good to go and we understand whatever has been said so far, just raise your thumb or give a thumbs up so that I can progress or move forward. Okay, so let's take a look at how we can do certain operations. Before we get to the Quantum Enigma, I want us to take a look at the poly S gate as a state vector. So we said the poly S gate is represented by the matrix, all right, 0, 1, 1, 0. I'm sure you're aware of this already, or better still, let me put in the matrix notation, the poly S gate. So if I want to represent the poly S gate as a state vector, I can easily do that. Remember, yeah, this is the poly S gate, this is a poly S gate. So this poly S gate is the same as this. So we have the bra being the row vector. You know, whenever we talk about bra, we are looking at row vector. When we talk about the ket, we are looking at the column vector. So always take note. Anytime I have something like this, 0, 1, this is a column vector. So, and this is a row vector. So always note the difference between the column vector and then the row vector. So this actually what you're seeing here is a column vector. This one is a row vector. This one is a column vector. This 0 is a row vector. So if I have 0, I can represent it as 1, 0 column vector. And if I have this one over here, this one can be represented as a 0, 1 vector. So that is how you can actually do that. But how about this 1 and this 0 that we have here? Remember the get notation and the bracket, realize that there are some differences. We have a situation where we are dealing with a column vector and a situation where we are dealing with a row vector. So let me go to a new sheet. So if I have this, I said this is the row vector. If I have something like this is actually this is a column vector and this is a row vector. So the column vector of this is 1, 0, all right? And the row vector of this is 0, 1. All right? So plus, if I have this, this is 1 and this is 0. So 1 here can be represented as a 0, 1 vector, and then the 0 here can be represented as a 1, 0. So always take note of the notations. This is a column vector and this is a row vector. So I can actually compute this, and then if I compute this, I'm going to get 0, 1, 0, 0 for this side, and for this side I'm going to get 0, 0, 1, 0. All right? And then if I add both, I'm going to get 0, 1, 1, 0. So realize that the poly X matrix can be represented as a state vector, actually. So we've actually derived the poly matrix even in a way. Yeah. So that is something we have to take note of, the differences between the row vectors and the column vector, so that we don't get confused whenever we are dealing with that. So on this note, I'll move straight to the Quantum Enigma as the assignment, the lab for today that we are supposed to do, just to explain some few things in there. Then from there, I'm sure you'll be able to handle the lab for today and do it to completion. All right. So let me share my screen. So yesterday I said you should watch the video regarding the treasure door. Yeah, Quantum Enigma 001. And then we actually, when you look at the video, it's talking about the fact that we have two doors that we are supposed to choose from, and one of the doors is correct and the other one is wrong. So we have two doors. One is a correct door, one is a wrong door. And behind each of these doors is a guardian. So there's a guardian next to each door, but one guardian only tells the truth. So how can we determine who is telling the truth? So that is a very tricky situation here. So what we need to do is that we need to find out actually who is lying, and how can we tell the guardian who is lying and the guardian who is actually saying the truth. So we have no way of knowing which is which, but then our job is to ask only one question to just one of the guardians and figure out which door is the correct door. So in the video, you realize that there was a way to translate the enigma of the two guardians into a quantum circuit, right? So let's try to build that circuit that the video was actually talking about. So we saw that the circuit contained 3 qubits. So the first qubit actually represents the first guardian on the right. The second qubit represents the second guardian. So, and the third qubit actually is representing the lie that gets told. So we want to represent one of the qubits with the first guardian, the other one qubit as a second guardian, then the third qubit, the lie that will be told, we want to actually represent that. So we don't know whether guardian 1 or 2 is lying for us. So we use that third qubit as a way to perform operations with each guardian to ensure we don't get caught in the lie. So if we don't want to get caught in the lie, then obviously we need to have a third qubit that we're relying upon. So the video states that we are actually supposed to put the first guardian into a state of superposition. So the first guardian, obviously also the first qubit. So we need to place it in a state of superposition. So to do that, I've explained that in order to place anything in a state of superposition, you need to use the Hadamard gate to do that. So it means that for the first qubit, if you want to place in a state of superposition, then we need to apply the Hadamard gate to it. Then we entangle the two guardians so they share information. This is the whole essence of entanglement, is so that two objects can share information, or two objects can have some form of correlation between them. So that is the whole idea about entanglement. So here we need to apply what is known as the controlled NOT gate, or the C0 gate. So, and now we should know the C0 gate. All right. Let me move to my so control NOT gate. This is the C0 gate. All right. That is how it is represented. If you want to program the C0 gate, you say maybe something like QC, that's a quantum circuit object, .cx, then you supply this with two parameters, right? The control qubit and the target qubit. So that is how to entangle. If I want to entangle two qubits, let's say the first is 0, the second is 1, then I can do so. So if you want to entangle, always use the control NOT gate to do so. Let's get back to our slides. All right. So we also put the lie qubit into a state of superposition. So the initial steps to this whole process for the Quantum Enigma, as the treasure door, you first have to apply a superposition to the first guardian. Then you entangle the two guardians, meaning you need to entangle the two qubits. After entangling them, now the third qubit, you also place it in a state of superposition. And that qubit is actually the lie qubit. So in effect, we just have to actually, for the first part of the circuit, we have to make a new quantum circuit with 3 qubits and 3 classical bits. As you can see from the diagram on the right-hand side, we now apply an H gate to qubit 0. All right. After applying the H gate to qubit 0, we also apply an H gate to qubit 2, as you can see from the diagram. And then we entangle qubit 0 and 1. So that is the first part of the circuit that we are supposed to do. Now we need to build a particular process, right? Now that we have our guardians and the lie qubit initialized. So this whole thing you are seeing is the initial steps of the initialization phases. Initialize the Q0 to the Hadamard gate, and initialize the Q2 also to the Hadamard gate. Then you apply a C0 gate to entangle those two qubits, that is Q0 and Q1. So after we are done with the initial phase, we actually need to build a process which will evaluate if a guardian is lying. So how do we look at that? So now, just for a reminder, the lie qubit measurement is how we know who is lying. So as soon as that third qubit, which is meant for the lie qubit, as soon as I measure that qubit, I should be able to know who is lying. That is the guardian. Which of them is lying? Either the guardian on the right or the guardian on the left. So when the lie qubit is measured as a 0, the right guardian is line. When the lie qubit is measured as a 1, the left qubit, the left guardian is line. Remember, these guardians are also qubits, so you have to take note of that. But with our lie qubit in a superposition, we won't know who is lying until the end. So until we have actually finished building our circuit to completion, we might not really be able to tell who is lying or not. So it's very, very important to build the complete circuit. Yeah. So we have now we are done with the initial part of the first circuit. The initial part of the circuit, which is the first part of the circuit. We have to take a look at the second part of the circuit. All right. Yeah. Basically, just create a barrier between all of these qubits. And after creating that barrier, that is the small lines you are seeing there in a vertical fashion. So these dotted lines you are seeing is the barrier. So you want to create a barrier, QC.barrier 0, 1, 2. That's how to create a barrier. So here, after creating the barrier, we need to entangle qubit 2 and qubit 1. So this is qubit 1, this is qubit 2. If I want to entangle these two, I use the C0 gate to do that. Now, subsequently, you see that you see a poly S gate here. So it means a poly S gate was applied to Q2. So we then apply a poly S gate to qubit 2, right? Then we have another entanglement here again. This time around, we are entangling qubit 2 and qubit 0. So we entangle those two. And then we apply another S gate again, poly S gate to qubit 2. So that is what this diagram is all about. So we have the first part of the circuit, and we have the second part of the circuit as shown. So there's an aspect of a truth table that you also have to employ whenever you are actually doing your lab. That is the lab on the Quantum Enigma. So it's easy to lose track of what we are really doing when encoding a problem into a circuit. So how do I remember which qubit is the guardian? All right, or how do I even know where the lie or the liar is coming from? So we need to actually deploy all of this in order to actually know who is actually saying the truth and who is actually lying and all of that. So in fact, we have to employ all of these gates because if we want to actually find some correlation between two objects in order to determine if a particular guardian is lying or not, then obviously we need some form of entanglement here in order to actually be able to say so. So that's how come you realize that this particular problem that we are trying to resolve or to solve, actually, as part of it, we use a C0 gate at various points in time because it's very, very important. So let's construct a truth table based on the video that was actually given. So some reminders before that, there are two guardians represented by two qubits. Remember I said that we have three qubits. One of the qubits is a guardian, the other is a guardian, and the third one is a lie qubit. So always place in your mind that Q0 is a guardian on the right, Q1 is a guardian on the left, and then Q2 is the lie qubit. So in effect, we have three qubits in this essence. All right. So how can we measure the guardian's qubits? When we measure the guardian's qubits, what is the meaning of that? So each time we measure the guardian's qubit and we get a 0, then that is telling us to pick the door on the right, right? So when you measure the guardian's qubit and you get a 1, and it's telling us to pick the door on the left. So how do we measure the lie qubit and its meaning? So we also have a third qubit, which I stated, the Q2, which we call the lie qubit, right? So when the lie qubit is measured as a 0, then the right guardian is lying. When the lie qubit is measured as a 1, then the left guardian is lying. So we basically have to use all of these information to actually construct some truth table that you are going to see shortly. So at this point, our circuit is just half done. We are halfway through. So that is the first part of the circuit, which was employing the poly S gates and the CNOT gate. So as a reminder, we have to take note of the following. So far as we are setting up a problem and asking the question, which door is the treasure behind? All right. So that is a question that we are always trying to ask. Which door is the treasure behind? We are trying to look for a treasure behind the door. But then behind these doors are guardians who are more like guarding this treasure, or behind the door guarding the treasure. But then we need to pose a question to them in order to try to find this treasure. Or we need to pose a question to them in order to actually know who is lying so that we can determine the truth, or we can decide to pose a question to them in order to ascertain the truth as to where the treasure is is either behind guardian 1 or guardian 2, or behind door 1 or door 2. So we need to actually establish all of that. So the first half of the circuit actually is only about establishing which is the correct door. So all that we've done so far, we're only trying to establish what the correct door is. But then the second half of the circuit, we must also ask another question. And the question is that, which door is the treasure behind? So that is very, very important. So let's always remember 0 means right and 1 means left. If you have this in mind, then you will not really get confused as we progress. So I can have a truth table here. So this is a lie qubit. Q2 is a lie qubit. Q0, Q0, and Q1 are the guardians, remember, all right? So we have a truth table as follows. So a 1, 0, 0, we have 0, 1, 1, 0, 1, 0, 1, 0, 1. So this is actually kind of confusing. Maybe let's see what is happening here. So one thing we have to note is that Qiskit uses little-endian ordering whenever it comes to the placement of the least significant bit and the most significant bit, and so on and so forth. So when I say MSB, I'm talking about the most significant bit. When I talk about LSB, I'm talking about the least significant bit, right? So a fancy way of saying that the most significant bit on the left and the least significant bit on the right. Right. So if we are reading the results like binary, we would start at the right and move all the way to the left. So realize that usually when you want to read something in quantum computer, especially when it's in a binary form, you normally have to read from the right to the left. From the right to the left. So you see that someone say, why didn't we start here with a Q0 so that we have Q1 here and we have Q2 here? It's because of Qiskit. Qiskit has been programmed in such a way that it uses what is known as the little-endian ordering. So we usually move from the right to the left. That is how the movement goes like. So if it is for our classical computers, maybe that might be something different, but that is how it is done in Qiskit. And so we just have to adapt with the approach that they are using. So Qiskit is saying that they did this on purpose, and then when you run an experiment and graph the results. So you can run an experiment based on all of this and also generate graphs of probabilities and all of that in order to see or to visualize your information. So that must be understood. Now in Qiskit, the qubits are represented from the most significant bit on the left to the least significant bit. So whenever we are representing qubits in Qiskit, we start off with the most significant bit, right, from the left all the way to the least significant bit on the right. That is how the arrangement is done. So this is similar to how we represent bits when it comes to classical computing, all right? And then this is to enable easy conversion and all of that. So that is very clear from that point. So let's look at this. So this should be much clearer now. We have various letter descriptions here, A, B, C, D. We have a guard on the right and a guard on the left. Remember, this is Q0, this is Q1, and this is Q2. I always said that 0 is right, and 1 is left. Always take note of that. So how can we explain this? So there's a descriptions of this truth table that you are seeing. So the description A is saying the treasure is on the right and the guard on the right is a liar. So treasure is on the right. So it's saying that the treasure is on the right and the guard on the right is a liar. That is what this whole description is saying. So the 1 here indicates that the treasure is here, but the 0 here indicates that this particular guard is actually a liar. So we have the B description. We have the treasure is on the right and the guard on the left is a liar. So we have the treasure on the right and the guard on the left is a liar. So yeah, various descriptions have been given for A, for B, for C, and for D. So anytime you use these descriptions against this truth table that you have here, you should not have a problem. I know it might be really confusing here and there, but be guided by the descriptions that we have here in order to view or to visualize this truth table that we have on top here. Other than that, you might get a little bit confused. So always use the descriptions as a guide, all right? Yeah, so let's pick our first one of the descriptions. So the guard on the right is saying the treasure is behind the door on the left, all right? So anytime we say Q0 is equal to 1, what we are trying to say is that the guard on the right is saying the treasure is behind the door on the left. Now, if we say Q1, if we measure Q1 and we get a 0, then we are saying that the guard on the left is saying the treasure is behind the door on the right. All right. So if we say Q2 is 0, then the guard on the right is a liar. So yeah, that is, you just have to be guided by the truth table we have here and these descriptions that we have here so that you do not get confused. So immediately after this presentation, I made these slides available. It is also in your lab. I think it has not been presented in a clearer form like this because maybe you have to do a lot of reading, but I actually put out certain things so that you actually view it properly. I'm sure viewing it on a slide is much more clearer. So yeah, so there are some practice tests that you can do. It's available in a lab file on Quantum Enigma. So you just have to follow all that you have done by designing the first part of the circuit, by designing the second part of the circuit, and by designing the third part of the circuit, which I have not shown here. I intentionally left that out so that you guys can actually think and then come out with that test circuit. As soon as you get a test circuit, then your whole work is complete and you are good to go. So yeah, so in order to finish the circuit, we need to remember the proper question from the video. The question we are asking is, which door would the other guardian tell me not to open? Or which door is the right door to go? So there are a number of questions that could be asked. But then we can ask this single question: which door would the other guardian tell me not to open? Right? Or better still, which door is the right door that is having the treasure? So there are questions you can ask in order to ascertain where the particular treasure is, or to ascertain which guardian is lying or not lying, and so on and so forth. So that is the whole concept about the treasure door and what it entails, right? So that is it. So you realize that in this particular lab, you make use of poly S gates, you make use of the swap gate, you make use of the controlled NOT gate for entanglements. Yeah, so that was one of the reasons why I explained the swap gate earlier on, because you're going to make use of it somewhere in your lab session for today. So always take note that the swap gate swaps the states of 2 qubits. If I want to swap the states of 2 qubits, I just have to use the swap gate to do that. So there is a function known as dot swap, and dot swap accepts 2 parameters. So we have the first qubit and the second qubit. I showed that on the IBM Quantum Experience Quantum Lab platform some minutes ago. I showed how to use the swap gate, that is swapping the states or contents of 2 qubits. So a swap gate looks similar to a CNOT, but instead of a circle on each end of the line, you see 2 X's. So yeah, so you realize that there were 2 X's on top of the line. We have a vertical line, we have an X on top, and we have an X down. So you see that, go to paint, you see that you have something like this. That is how the swap gate looks like. So if you look at the quantum experience, let me go to that platform. You see the swap gate, vertical line with 2 X's below the line, which means that we are trying to swap 2 things. That is the indication. So to use the swap gate, you say dot swap. Dot swap. Always use the dot swap function. So the Qiskit, as soon as you actually create your circuit and you create a circuit object and all, that circuit object has a function called dot swap. So you supply the dot swap function with 2 parameters, or the 2 qubits that you want to swap. So as soon as you perform a swap, the states of those 2 qubits will be interchanged or exchanged. So if you look at this diagram, as I said again, I initialized this state to a 1 state, and I initialized this state to a 0 state. So I performed a swap. So if I perform a swap, then Q1 should now get Q0's value, and Q0 should get Q1's value. That is what we are basically trying to do. So when you measure, you should be able to see your desired outcomes, all right? And to measure, you say QC dot measure. I think we looked at this yesterday. QC dot measure, and this measure, you supply it with 2 parameters, which are lists. The first list, right? If it's just a 1 qubit, then there's no need to be a list. Assuming that we are dealing with 1 qubit, obviously we just have something like measure 0 on 0 if we're dealing with a 1 qubit. But because we are dealing with 2 qubits, so you have to actually put this in a list form, 0, 1, and 0, 1. If we are looking at 3 qubits, that is, assuming I was trying to measure something based on 3 qubits and 3 classical bits, it's going to be something like this. So my first list contains 0, 1, 2, 3 qubits, and the second list 0, 1, 2 classical bits. So that is how we can perform measurements in Qiskit. So always take note of that. All right, so we are going to utilize the swap gate. We're going to utilize the C0 gate. We're going to utilize the poly S gate for the Quantum Enigma lab for today. So let's finish with our slides. Yeah. So finishing the circuit, you actually have to go through this process, part 3. So I showed you the part 1, part 2. This is the part 3. All you need to do is just create a barrier and apply these gates in this order, and your circuit is done. You're good to go. So you apply a swap gate to qubit 0 and 1. Then you apply a poly S gate to qubit 0, and you apply a poly S gate again to qubit 1. You entangle qubits 2 and 1. You apply a poly S gate to qubit 2. You entangle qubit 2 and 0. Then you apply a poly S gate to qubit 2. So based on all of this information and knowledge that you have seen, I'm sure you should be able to do your labs with ease and without any problems or hindrances. Yeah. So you now have a complete circuit at this point in time. All right. So you can actually visualize your circuits and even look at graphs, the histogram, and actually view the probabilities of information that is actually showing up. All right. So that is it for the Quantum Enigma. All right. Are there any questions before I hand over to Dorcas?
Please, if you have a question, you can unmute yourself and ask directly as well. Questions, please.
Well, I think it is either it's kind of clear. So sure they shouldn't have any problem with the lab if they follow the guidelines that have been given in the lab, and as well as these slides that I will be sharing with you. So all the best lab. Yeah. So Dorcas, I hand over to you. Yeah.
All right. Thank you so much, Dr. Nimbe. That was a very wonderful presentation and very explanatory as well. And since there are no questions then, I guess we all had it at a go, and I mean, it was very understandable to all of us. So thank you so much. To our participants, the labs and his slides will be made available to you. So we'll put all that on our GitHub So kindly do check on the GitHub to download the slides and the lab he shared with us through this presentation. And as well, today we are submitting our graded lab B. And the deadline is today. The time is 11:59 p.m. GMT. Kindly do not submit lab C, just lab B for today, please. And when you finish solving on the IBM Quantum platform, you are supposed to download the lab, then you rename the lab. So your full name, then the lab, don't forget the extension as well. Then you upload onto the Google Drive link we shared with you on WhatsApp. We'll share the link with you through your email again so that everyone can have access to it, especially for those who have not joined the WhatsApp page. It was great having you join us for this session. We look forward to seeing you tomorrow. Tomorrow we'll be talking about dynamical circuits. We'll have a lecture as well, then a lab session. And that is also to prepare us to solve lab C graded assignment. So thank you so much. But one last thing before we go off, I guess we need to take a snapshot. So, Dr. Nimbe, if you don't mind, you can stop sharing your screen with us.
Okay. Yeah.
All right, so let's get a snapshot today. Okay, wonderful. So this is Qiskit for First Ghana chapter. You may be wondering why we are online. It's because school is on vacation and most of our students are home. So it will be very difficult trying to get students to come to campus. That's why we are online. We are hoping that next year we can go in person. Can we take it now? It looks like more people are still trying to put their videos on. Okay, so maybe you can give us a quantum smile, a Qiskit smile. Since we are all energized now. Okay, so the first shot, the second shot, let me take a last shot. Great. So once again, thank you so much. It's great having all of you around here. On Friday, we'll crown everything on Friday. So on Friday, we have the closing ceremony and our challenge. We are urging our nationals, especially the Ghanaians, to actively be involved in this challenge since we have a package for you aside all of us getting a certificate. It was great seeing all of you. So we'll meet again tomorrow. Thank you so much. Bye.